Okay, so greetings everyone and welcome to our first online lecture of the semester. Before I begin, I wanted to take a second and say that I hope that everyone and all of your families are doing well and are safe during this whole situation. I know that the COVID-19 pandemic has put many people's lives in turmoil and at a minimum has changed all of our daily lives and routines. And so I want to assure you all that I recognize that this process moving forward is going to be a challenging one and will also need to be a dynamic one. So I have an initial plan of how this course will proceed, but I definitely will be reaching out to you at the end of the week to gather feedback regarding things that I can change or add that will aid in the digestion of all of the course material that we still have ahead of us before the end of the semester. With regards to homework, I'm not necessarily sure how I'm going to approach that moving forward, but I will let you know as soon as possible. And I am not exactly sure how in terms of making myself available for questions and office hours, that will proceed. I imagine it's going to be some combination of emails plus Zoom or some other type of interfacing software that will allow for a more direct, engaged interaction between you all and myself. So, with that said, today's lecture will be our first discussion into heat transfer. Heat transfer and the equipment related to heat transfer are integral parts to many chemical processes, and therefore understanding heat transfer and heat transfer equipment, that is, heat exchangers, is critical to your education as a chemical engineer. And so in terms of heat transfer, we are going to start by talking about the different modes of heat transfer, excluding radiation, which we will leave to the end of the semester. We will move into different types of heat exchanger or heat transfer equipment, talk about sizing heat exchangers. We will then move back into shell balances and talking about deriving heat transfer equations for particular scenarios, and finally ending on a discussion of radiative heat transfer. So today's lecture, the primary focus of it will be to talk about the conductive heat transfer mechanism. But before we get into that, I just want to quickly go over the three different types of heat transfer that we will cover in this course. The first of these is what's known as conduction. And conduction occurs in both fluids and solids. And conduction is a molecular process that's characterized by this thermal conductivity. Right? We think about conduction through the following equation. Right, so this is going to be our term for heat conduction, and we have here heat conduction in the x direction is equal to the negative of our thermal conductivity multiplied by our temperature gradient. Right, so in this case, our temperature gradient is dt dx. This equation is what is known as Fourier's law of heat conduction. And the typical units on this parameter, so in terms of English units, you have BTUs per hour foot squared, or in SI units, watts per meter squared. Okay, and a watt is simply a joule per second. Right, so this term here, oh, it's a little thick. Right, this term here is our heat flux. Right? And if you remember, I said that flux is simply a term that represents the flow rate of something per unit area. Here it is the flow rate of heat per unit area, hence BTUs per hour per foot squared, or watts per meter second, or you can think about that as a joule per second per meter squared. And so that is conduction. And the other thing I want you to take away from conduction is that conduction, right, it occurs, oh, that's not right, it occurs within a fluid or a solid. Right, so we're going to be talking about heat transfer to and from a fluid or solid, and we're going to be talking about heat transfer within a fluid or a solid. Right, so just keep in mind here that for us, conduction, right, we're referring to heat transfer within a solid or a fluid. Right, the other type of heat transfer that we will talk a lot about in this class is convection. This says in fluids. I would get rid of in. I would make that involves fluid flow, right, which is essentially what I'm saying following here, is that it is associated with fluid motion and characterized by a convective heat transfer coefficient, H. Right, so in order for convective heat transfer to occur, there has to be some type of fluid motion. Right, so a simple example would be I have a heated piece of metal and I am flowing air over it to cool down that piece of metal. Right, I am convecting heat away from that solid piece of metal by flowing a colder fluid over it. Right, so conduction, that's going to be within a fluid or a solid. Convection is going to be heat transfer to a surface or away from some surface, and it's because there is fluid motion that that convection is occurring. Right, there are two types of convection. The first of these is called forced convection. So that is when you are forcibly moving a fluid over something to either heat it up or cool it down. Right, so the the example that I just gave of blowing air over a hot piece of metal to cool it down, that is an example of forced convection. Right, the other type of convection we will have, or you will run into, is natural convection. Right, natural convection is convection that occurs naturally, i.e., it occurs due to some fluid motion that is occurring without an outside force. Right? So an example of that would be air, right? Having some current of air because of density differences of the hot air and the cold air. So the hot air rises. As it rises, it starts to cool down. As it cools down, it gets more dense and starts to fall, heats up again and rises, right? And so that's a natural convection cycle. It occurs because of density differences in the fluid itself. For us, convection is represented by Newton's law of cooling, which looks like this in a general form. Right, this is Newton's law of cooling. And in this particular example, I am assuming that my surface is hotter than my fluid. Right? My heat transfer is going to occur from hot to cold. Right? So if the fluid was hotter than the surface, then these two terms would be reversed, or right, you could add a negative in front of there to indicate the direction of heat transfer. But in a general form, our convective heat transfer equation is simply the heat flux is equal to the convective heat transfer coefficient times this temperature difference between the surface and the fluid, or the fluid and the surface, just depending on which one of those is actually the hotter material. All right, and lastly, we have radiative heat transfer, and this takes place in the form of electromagnetic waves. And for us, the most important thing, or the biggest thing I want you to take away from radiative heat transfer is that it's characterized by this emissivity, right? And that emissivity pops up in our heat flux equation. So our heat flux is equal to the emissivity times a Stefan-Boltzmann equation multiplied by temperature to the fourth power. Right? That's also a very, very important thing to take away. Right? If I compare all of my forms of heat transfer, radiative heat transfer is the only one, right, where my temperature goes to the fourth power. Right? So this equation again is called the Stefan-Boltzmann equation. Where this is our Stefan-Boltzmann constant. Okay, so 3 different modes. Conduction. Conduction occurs within a solid or a fluid. Convection. Convection occurs to and from some surface. And then we have radiative heat transfer, right, which is characterized by an emissivity, and our heat flux in terms of radiative heat transfer goes as temperature to the fourth. And like I said, we will cover radiative heat transfer in a bit more detail if we have time at the end of the semester. But, definitely want to make sure that we get through conduction and convection, because those are going to be our 2 most common forms of heat transfer that you will run into in the chemical industry. Okay, so I know I said this in the past minute or 2, but I want to point this out again. Please note that heat transfer occurs from a hot surface or area to a cold surface or area. Right? Much like when we were talking about fluids and momentum transfer, right? We had that momentum transfer from an area of high momentum or high velocity to an area of low momentum or low velocity. So, same thing going on here. Now we're just talking about heat. Okay, so let's get into our discussion of conduction. What you have here is a homogeneous slab or planar slab of material, and that material is initially at a uniform temperature T sub naught, and the thickness of this slab is H. Now we're going to imagine a scenario where we suddenly raise the temperature on the top surface of the slab while maintaining the temperature on the bottom surface at T sub naught. Right? So in this case, we have our slab. we are holding the bottom surface still at T sub naught. And we have now, let me get rid of that, increased the top surface to T sub 1. And so our temperature profile, right, much like a velocity profile, the temperature profile tells me how the temperature changes as I move through the thickness of that slab. Looks something like this right after I change the temperature. So initially, I do have some temperature change at the top of my slab close to the top of my slab within my material. After waiting a sufficient amount of time, i.e. waiting until steady state is achieved, I can then reevaluate my temperature profile. So again, bottom surface is held at T naught. And top surface at T sub 1. So what you can see here is based on the geometry. I have a slab or a planar material. Right, what I end up with here is a linear temperature profile through the thickness of my slab, where the temperature varies from T1 at the top surface to T naught at the bottom surface. Experimentally, it has been shown that the heat flux through the slab is proportional to that temperature gradient across the slab. What do I mean by that? So in our scenario, heat flux in the y direction is equal to the heat flow in the y direction divided by our area. So this term here is heat flow. That is proportional to the temperature difference between T1 and T naught. Right, and the thickness of our slab. Here I have a negative because heat flows in negative y direction. That is, heat is flowing from the top surface at y equals h to the bottom surface at y equals 0. Right? So my heat flow is moving in that direction. The constant of proportionality relating that heat flux to the temperature gradient in terms of conduction is what is called the thermal conductivity. Right? So you can think about this like shear stress in the sense that the viscosity is what relates the shear stress to the local velocity gradient. Here, our thermal conductivity is the proportionality constant that relates our heat flux to our temperature gradient. So heat flux in the y direction, which we know is heat flow in the y direction divided by the area, is equal to negative K T1 minus T naught divided by H. We can take that equation, write it in a differential form, yielding the following equation. Right, which is the same equation that we saw on the first page. And again, the equation that we have in that box is what is known as Fourier's law of heat conduction. Below that, I have some typical values of thermal conductivity. As you might imagine, right, metals are more conductive than things that are made of wood. Water is actually relatively conductive because of the ions that are in it. And then we have something like air that is orders of magnitude less conductive than a solid like steel. This low conductivity here is the reason why we have double-paned windows. Right? We have now between those two panes of windows a fluid like air, where air is not very conductive at all. Okay. I actually think that this is double pane windows, but don't quote me on that. This is air. Okay. Oftentimes, right, especially when you are dealing with different materials, you run into heat transfer through composites, right? So what you have here is a simple schematic of a composite. We have composite 1, composite 2, and composite 3. And so in this figure, or schematic, what I'm showing is on the far left-hand side, I have air. And that air is hot and is at a temperature T sub H. I have a surface temperature on the left-hand side, and that is going to be T sub 1. Then I have conduction through my solid. I reach the interface between material 1 and material 2, and now I have my temperature T sub 2, right, so on and so on. So we reach T3, T4, and then on the right-hand side we have our cold air at a temperature T sub H. This drop and increase in temperature, right, this is right, heat convection. Again, we talked about Newton's law of cooling. I mentioned Newton's law of cooling. I'm not going to focus very much on the specifics of that part of this problem, right, because I want to focus on convection through these solids, conduction through these solids. But keep in mind, right, the reason that you have this temperature drop from hot to T1 and temperature increase from T4 to TC, the temperature drop from T4 to TC is due to convective heat transfer. Okay, so first thing we will do is we will start with Fourier's law of heat conduction in the x direction. If we assume that the area through which heat conduction occurs, as well as the thermal conductivity, is constant, then at steady state, our heat flux is also constant. So we can write that for the first slab. Right. Heat flux in the x direction through slab 1, heat flow in the x direction through slab 1 divided by the area, so our heat flux here. This is constant, so I'm able to move it outside my integral. My thermal conductivity is constant, so I move it outside my temperature integral. And so again, I have just rearranged Fourier's law of heat conduction and taken the integral through the thickness of the slab as well as over the temperature difference through the slab. So I perform that math. I end up with x1 minus 0, all of that being equal to K1 T1 minus T2. Right, I've lost my negative here because I have switched T1 and T2 with each other. Let me get rid of that negative, or excuse me, that circle before it confuses someone. All right, I'm going to rearrange that equation a little bit. And so for us in this particular scenario, the heat flow in the x direction through slab 1 is equal to the thermal conductivity of slab 1 multiplied by the area through which that heat transfer is occurring. And all of that is multiplied by our temperature difference across the slab divided by the thickness of our slab. So again, what I've done here is I've taken Fourier's law of heat conduction and I've used it to derive an equation that describes the heat conduction through slab 1. Similarly, I can do that exact same thing to describe the heat conduction through slabs 2 and 3. So I have heat flow in the x direction through slab 2 divided by the area, all of that equal to K2 T2 minus T3 divided by x2 minus x1. Right, that becomes a very similar equation to the one you just saw. I can do the same thing for slab 3. And end up again with a very similar equation to the two that I just derived. I mentioned this on the last page, but at that solid air interface, right here and here, I have convective heat transfer occurring. Again, conduction through a fluid or solid, convection to or from some type of surface. So at that air-solid interface, we can use Newton's law of cooling to represent the heat transfer. Again, I don't want to get too far into convection at this moment, so just generally, our heat flow in the x direction is going to be equal to our convective heat transfer coefficient H, the area through which that heat transfer is occurring. And on the hot side, well, I'll write this, this is where I want to write my general form, so Ti minus Tj. Specifically for the hot side, I have my heat flow on the hot side is equal to the hot side convective heat transfer coefficient times my area of heat transfer. And now I'm just going to ask myself, which is the hotter temperature, TH or T1? Right? It should be obvious that TH is the hotter temperature. Heat transfer occurs from high to low temperature. So I end up with my temperature difference as TH minus T1. I can write an analogous expression and an analogous expression for the cold side. And here, the temperature at that wall, T4, is hotter than the cold temperature of the air on the right side of my composite, so I write my temperature difference as T4 minus Tc. And I know that at steady state, my heat flow, or heat flux, in this case, is constant. So my heat flow is equal to heat flow in the x direction through slab 1, heat flow through slab 2, heat flow through slab 3. These should be equals, not additions. Equal to. That is going to be equal to my convection at the hot and cold surface. Again, all of this is because I am at steady state. And so now I've written out that equation in terms of convection and conduction to and from my composite, as well as within my composite. If I go back to my figure here, what I see are these two temperatures at the interfaces or within my composite. And so I ask myself, okay, in reality, how can I actually determine what those temperatures are? Right? And so in reality, determining those temperatures is not straightforward, but we can do a bit of mathematical manipulation of our equation to show that we don't actually need to know what those temperatures are to determine the overall heat flow in our system. If we take all of those equations, and here I've simply rearranged those equations and solved for the temperature difference. I take all of those, I add them up. Right, what you will see is I have a negative T1, a positive T1, negative T2, positive T2, and so on. All of my temperatures at the wall or between the walls cancel out, and I'm simply left with the temperature on the hot side of my air and the temperature on the cold side of my air. All of that is equal to the heat flow times 1 over convective heat transfer coefficient on the hot side, and then all of my conductive terms and finally the convective term on the cold side of my composite. I'm going to rearrange that equation and solve for the heat flow. And I get that the heat flow is equal to TH minus TC. Convective term on the hot side. Convective term on the cold side. And then between those, I simply have the sum of my conductive terms within my composite. And that is the equation that describes heat flow through that three-material composite. And what we see from this final equation and what we saw as we worked through this derivation was that we don't actually need to know any of the temperatures. We don't need to know T1 through T4 to be able to talk about the heat flow in our system, as long as we know the temperature of the hot air, the temperature of the cold air, and of course things like the thermal conductivities of our material, as well as the convective heat transfer coefficients on the hot and cold side of our material. What that equation really points at, or makes us think of, or should make us think of, is, or you will see, I'm not sure how many of you have sat through an ECE class, but I know that we do have an ECE class as part of our curriculum, so you will eventually sit through an ECE class. What we see here with heat transfer is analogous to electrical circuits. So in this case, our electrical circuit, we have some voltage, and then between E1 and E2, we have a number of resistors. So the heat flow, the current or the flow of electricity is analogous to our heat flow. The delta E that you see from E1 to E2, that voltage drop is analogous to our temperature drop. And in the terms of the resistors that you see in the schematic above, the resistances or resistors in our system are convection to and from the surface of that composite, as well as all of the conductive terms within the three different materials of our composite. So in reality, or in a more succinct form, we can write that our heat flow is simply our delta T divided by the sum of our thermal resistances. What you will come to find, or what you will come to see, is we will start to think about things in terms of an overall heat transfer coefficient. This overall heat transfer coefficient we are going to term capital U. And for us, capital U is equal to the heat flow divided by the area through which heat transfer is occurring, multiplied by our temperature gradient. So if we take our equation above, plug it in here, what we find is the overall heat transfer coefficient is equal to 1 over the area times the sum of those thermal resistances. Here next to that, I have shown typical units of the overall heat transfer coefficient. So the only difference in terms of units between our overall heat transfer coefficient and our, go back to the first page, our heat flux is delta T. Because again, heat flux is simply heat flow divided by area. So there's our heat flux. We divide that by a temperature, and we get our overall heat transfer coefficient. And so following that, you get units of heat flow per area per degree. Right? So BTUs per hour per foot squared per degrees Fahrenheit, or watts per meter cubed Kelvin. Okay, hopefully what I have talked about so far has made sense. Let me highlight or summarize a couple of the main things that I think you should take away from this lecture. 1, conduction. Conduction is a mode of heat transfer, and it is heat transfer that occurs within a fluid or a solid. Conduction is described by Fourier's law of heat transfer, right, and characterized by the thermal conductivity, or K, of the material. Then you have heat transfer by convection. Right? Convective heat transfer always involves the flow of some type of fluid. Right? And convective heat transfer occurs to and from the surface of a fluid or a solid. There's also radiative heat transfer. Really the main thing I want you to take away from that is that the heat flux goes as temperature to the 4th power. And we will discuss radiative heat transfer in more detail later. So, in order to hammer home the point of heat conduction, I want to go through the following example problem before I sign off today. In the following example problem, I have the wall of a house. It is 7 meters wide, 6 meters tall, and 0.3 meters thick. It is made of brick, and the thermal conductivity of that brick is 0.6 watts per meter Kelvin. The surface temperature on the inside of the wall is 16 degrees, and the surface temperature on the outside of the wall is 6 degrees. So Ti 16 degrees, and then on this other surface To is 6 degrees C. Okay, so we have a winter day. It is a lot warmer inside your house, hopefully, than it is outside your house. In this particular problem, you can think about this one of two ways. Right? The better way to think about it is that the actual surface temperature here is 16 degrees C, and on the other side, the actual surface temperature is 6 degrees C. Right? What I mean by that, if I go back to my composite example, let me erase. Right, so what I mean by that is that the inside and outside temperatures that I'm showing in that problem represent T1 and T4, or you think about it by saying that TH equals T1, TC equals T4. Right, and what the implication of that, is that my convective heat transfer coefficient is a really, really high number. Right? The higher that number is, the better convective heat transfer coefficient is, the less the temperature difference between my T hot and my surface, and my T4 and my T cold. Right? So in our particular example, we are saying that literally the surface on the inside is 16 degrees and the surface on the outside is 6 degrees. Therefore, we are ignoring, let me write that down, we are ignoring convective heat transfer. Okay. The problem asks us to find the heat flux as well as the total heat loss through the wall. To find the heat flux, we are going to start with Fourier's law of conduction in the x direction. I guess the direction is irrelevant. I haven't defined any coordinates here, so we'll just say the heat flux. That is equal to the negative thermal conductivity multiplied by our temperature gradient. In our particular case, the temperature gradient is the temperature difference between the inside wall and the outside wall. And dx is simply the thickness of our wall. I know the values for all of those, so I'm going to plug those in. Thermal conductivity is 0.6 watts per meter Kelvin. That is divided by the thickness of my wall, which is 0.3 meters. And that is multiplied by my temperature difference. So when I carry that math out, I get that my heat flux is equal to negative 20 watts per meter squared. Right, if you noticed, I left these temperatures in terms of Celsius because here I'm talking about a delta T. Right, and every delta T in degrees Celsius is equal to the same delta T in Kelvin, so I don't need to convert those because I'm talking about a temperature difference. Just to point that out. The last part of the problem says calculate the total heat loss through the wall. And we calculate the heat loss. What they're asking there is actually to calculate this heat flow. What is the speed at which heat is flowing? A joule per second. That's what we're looking for here. We know if we rearrange Fourier's law of heat conduction that our heat flow is simply equal to our heat flux multiplied by the area through which that heat transfer is occurring. Our heat flux is negative 20 watts per meter squared, and that is going to be multiplied by the area through which heat transfer is occurring, which is simply going to be the area of our wall, which is 6 meters tall, 7 meters wide. So that is 42 meters squared. And we end up with our heat flow or heat loss through the wall of 840 watts. We need to put a dot there for 2 sig figs. Box that answer in. Right? So that is how we use Fourier's law of heat conduction to calculate things like heat flux and heat loss or heat flow. This is heat flow through this solid wall. Again, I'm going to say this one last time. Conduction occurs within a fluid or a solid, and convection occurs to and from the surface of some material. Okay, so thank you all for joining me for this first online lecture of the semester. Hopefully everything I said made sense. You have this video. Please rewind, go back, look at the things that I've written along with the things that I've said. If any of those things do not make sense, please reach out to me, ask questions. I don't want anyone to fall behind because they didn't understand something that I've gone through in these early notes. Again, we're setting the stage here by talking about conduction and convection, leading into the idea of talking about heat transfer equipment, in other words, heat exchangers. So, with that, I am done talking, and I hope everyone has a great rest of the day.